Hey guys, I'm Lauren Greenberg, and today I'll be doing problems 29b and 37b about the common ion effect and buffers. The common ion effect plays a role in decreasing the solubility of solids, and this is due to the addition of common ions that cause a shift in equilibrium. The common ion effect also plays a role in the regulation of buffers. Buffers resist pH change by neutralizing added base or acid. Problem 29b says, solve an equilibrium problem using an ice table, or as we say in class, a rice table, to calculate the pH of each solution. A solution that is 0.16 molar in NH3 and 0.22 molar in NH4Cl. So, we must make an equation with what we are given. R stands for reaction, which is NH3 plus H2O, which yields H3O plus NH4Cl. The buffer is a weak base, which is NH3, or ammonia, and its conjugate acid is NH4Cl, which is ammonium chloride, with Cl being the common ion. Next, I stands for initial concentration, so we put in the initial concentrations given. For NH3, it's 0.16 molar. For H2O, it's a solvent and a liquid, so we leave that alone. And for H3O, we aren't given the concentration, so we assume it to be 0. And for NH4Cl, we are given 0.22 molar. For C, this is the change in concentration. We indicate this with a negative x on the left side of the equation and positive x on the right side of the equation. E is the equilibrium concentration, which is the I and the C added together. So for NH3, it's 0.16 minus x. For H3O plus, it's x. And for NH4Cl, it's 0.22 plus x. Once this is complete, we find the Kb value, or the equilibrium constant, of NH3 in the back of the textbook. The Kb value of NH3 is 1.76 times 10 to the negative 5. We make an equation for the equilibrium constant by substituting the equilibrium concentrations of products over reactants. So this is 1.76 times 10 to the negative 5 equals x times 0.22 plus x over 0.16 minus x. In order to find the x, we cross multiply. We find the values of a squared plus b minus c. The a value is 1, the b value is 0.2200176, and the c is negative 2.816 times 10 to the negative 6. We use the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. For the sake of this problem, and the x value, for the x value to be positive, we use the plus sign and we don't use the minus sign in between the negative b, and the square root of b squared minus 4ac in the quadratic formula. So we solve for x, and we get x to be 0.000012798. With this x value, we assume it to be the OH, because NH3 is a base. So we find the POH by using the equation POH equals negative log of OH. We plug the x value that we just found into the OH and find the POH to be 4.892857894. In order to find the pH, we use the equation pH plus POH equals 14. So now we plug in the POH value that we found, and we find the pH to be 9.1, which is two significant figures, and we rounded it at the end. 37 says, use the Henderson-Hasselbalch equation to calculate the pH of each solution in problem 29. The Henderson-Hasselbalch equation is pH equals pKa plus log of base over acid. First, we have to find the pKa. So we know that the Kb of NH3 is 1.76 times 10 to the negative 5. And the Kw is a constant, which is 1 times 10 to the negative 14. So we find the Ka to be 5.68 times 10 to the negative 10. With this, we use the equation pKa equals negative log of Ka. So we plug in the Ka value that we just found and find the pKa to be 9.25. Now, we can plug in our known values into the Henderson-Hasselbalch equation. So the pH equals 9.25, which is the pKa, plus log of the base, which is the initial concentration of NH3, which is 0.16 molar, over the acid, which is the initial concentration of NH4Cl, which is 0.22 molar. And we get the pH to be 9.1, which is 2 sig figs after rounding. So, as you can see, these are two different ways to find the pH of a solution, one using the Rice table and another using the Henderson-Hasselbalch equation. Thank you for listening.